So, as we do at the beginning of each class when on days that homework is due, are there any questions? Actually, we answered a few questions before we turned on the video. We should probably wait until the video starts to answer questions. That way people can... That's fine. That's fine. So, are there any questions?
You put that on C. No.
You asked, some people came by my office and got some little questions squared away. And anyone? We're all good to go? You ready to? Did you get caught up very much, or did you?
Yeah, I just have 1.3 to do.
Okay, good. But did you check the lecture, the recorded lectures on iTunes?
Yeah.
Good. Good. All right. If there's no, Ben, any questions about the homework?
Is it due?
Is it due? Well, those aren't the kinds of questions that I expected to have to answer today. The answer is yes, it's due, and because today is, you look on the syllabus and it's all scheduled out, right?
I just want you to know that I care about this class. I do homework.
That's wonderful.
I read the book, unlike my other classes.
We got. I just want to show you 2 more slides before we go on to the next chapter. Table 1.2 in the book gives us examples of multiple assignments. So in this table, this is not textual substitution. This is a programming statement. So this is an assignment statement. And in our programming language that we're going to use in this course, we're going to talk about it in more detail later. The name of the language is the Guarded Command Language, GCL. And in this programming language, you can actually do multiple assignments. If you say x comma y gets y comma x, that happens simultaneously. And what it does is, whatever value y has, x gets that value, and whatever value x has, y gets that value. And it can happen simultaneously. Now, you can't do this in either C++ or Java. Like if you're learning, when you're learning in C++ and you do the assignment statement. Now, do you remember what the assignment statement is in C, what the symbol is in C++?
Equals, equals.
No, that's equals equals is equals.
Equals is assignment.
Equals is assignment. So in Java, if you say x comma y gets y comma x, you can't do that. The compiler will complain and it will not work. And you can't do this in C++ or Java. But you know what? There is a really cool language, I mentioned it before, called Python. And in Python, you can do this. Yeah, it's the newest of the 3. And so it's really kind of slick that way. And here's x comma y gets 0, 0, so that's x gets 0 and I gets 0. And I comma x gets I plus 1 comma x plus I. Now, maybe we should do an example with state on this one. Suppose the state is I for x 10. Suppose with this one, the initial state is I for x 10. And then suppose we do I comma x gets I plus 1 comma x plus I. What's the final state? The final state is going to be I something x something.
I 5 and x 14.
Well, yeah, the question is what?
I 5 and x 15.
Everyone agrees that it's I5, right? Because I gets I plus, but it's simultaneous. So when we say x plus I, is it x plus this I or is it x plus this I?
First I.
It's the first I because it's simultaneous.
Yeah. So before anything's changed, it does all of them. Basically.
Yeah, that's what we mean by simultaneous.
Cool.
Is everybody clear on that? So add 1 to I and add I to x. But we're adding this I to x. So what's the final value of x?
14.
14, not 15. Is everybody clear on that? How that works? Now, like I say, you can't do this in C++, but you can do it in GCL, in this language that we're learning in this class. And here's x comma I gets x plus I comma I plus 1. Now, this is interesting. Is this going to give us, if we have the same initial state, are we going to get the same final state as we did before?
Yeah, it's simultaneous.
It's simultaneous. Yeah, so it's going to be the same initial. If we have this initial, we do that, that's the same final. So everybody clear on this? How this works? So don't try this in your C++ class. It won't work. Well, I mean, actually, the way we are doing it is, we're doing it like this, right? In our language. And now just one more slide before we go on to the next chapter. Here are 3 examples of the Hoare triple that we learned yesterday, or day before. So here we have, so let's just suppose that this was blank, right? And suppose we have this post condition, x is greater than y, and we have this statement, x comma y gets y comma x. Now do you remember the rule that we had for calculating the precondition?
Go backwards.
You go, yeah, and you do textual substitution, right? You take this as if it were textual substitution and you apply it to this, right?
Yep.
Does everybody remember that? So what this says is you take x is greater than y, and x turns into y, and the y turns into x. So there you have y greater than x for the precondition, right? And it doesn't always have to be all on the same line. Does everybody understand that this whole thing is the precondition, and then this whole thing is the statement, and then this whole thing is the postcondition? Are you with me on that? Okay, so they can be on separate lines. Is the statement, right? And so what we do is we do textual substitution of this into the postcondition, right?
Yeah.
Okay, so let's write down what that is. What do we have in the postcondition? We have x. We have x. So in place of this x, what are we going to get? X plus I. So this is going to be x plus I, right? And now, in place of this 1 plus 2 plus dot 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 plus I minus 1, this is going to be 1 plus 2 plus dot 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 plus. But now, instead of being I minus 1, this I is going to be I plus 1. So this is going to be I plus 1 minus 1. And sure enough, that's what we have up here. Yes?
What I want to know is why you have the post condition before you have the precondition.
You do, yeah. See, that comes about by remember what we said the definition of assignment was? We said the definition of assignment is this. R with x replaced by e, and then here is x gets e, and then here is r. And what happens is the precondition comes first, then the statement, and then the postcondition, right? And here what we have is the precondition comes first, and then the statement, and then the postcondition. Did that answer your question?
Well, like, why is it that way? Like,
Why is what? You mean why is this that way?
yeah, why is
Yeah, we did a few examples. Go back and check the examples that we did yesterday. We did some examples. Remember over here on this side of the board we had some blank preconditions, and we did that textual substitution, and sure enough it made sense.
Yeah.
Oh, and why did it make sense? Because we know what the interpretation of the Hoare triple is, right? So what's the interpretation of the Hoare triple? P,
It's true.
S, Q. What is it? What is it?
If P is true,
If P is true, and you execute S, S terminates, and Q is guaranteed to be true. So when we did that, we saw some examples of how that made sense. Yeah?
So we guarantee Q to be true by...
Yeah. If you do that textual substitution of the statement into the postcondition, you get a precondition such that if that's true and you do that, the postcondition is guaranteed to be true.
Okay. So we're guaranteeing
Right. Okay, well, so there's a homework assignment for Monday. Has an exercise with these Hoare triples just to calculate the precondition given the statement and the postcondition. But it's just a simple textual substitution, so it's not too complicated. Now, okay, we are getting closer and closer to that fateful day when chapter 3, like I said, is when the story really starts. Today what we're going to do is we're going to learn about Boolean expressions. Now, all of the examples that we've done so far with textual substitution, all the examples that we've used have been examples from algebra, because you guys already know algebra. You know A times B equals B times A. You know how to do algebra. So that's been our examples. But what we're going to learn today is a system of a mathematical system called Boolean algebra. And specifically, we're going to learn what is a Boolean expression. Right? Now, yeah, what's the first part of the definition of an expression? An expression is either a what or a what? A variable or a constant. Well, guess what? There are only two there are only two constants in a Boolean expression, and those two constants. Somebody said it. True or false. So the constants are true, false. Now you know our book abbreviates these as T and F and uses lowercase, but I would prefer that you use uppercase. So on your papers, indicate true by uppercase T and false by uppercase F, all right, if you want to abbreviate it. You can spell it out if you want, but. Okay, and the reason is lowercase t's and lowercase f's, I've learned over the years that on a lot of papers I can't tell the difference with your handwriting. It's a lot easier for me to grade your papers if you use uppercase for T and F, right?
Doesn't programming execute to like show true in capitals? I feel like
yeah, you know, it depends on the programming language, how it
Java does.
Yeah. But anyway, T and F, okay, for true and false. All right, so those are the constants. Now, and then there is one unary operator. And the unary operator looks like this. We've mentioned this once before. What does this mean?
Negation.
Yeah, negation, or negation,
Not.
also called not. Okay, so that's the not operator. And it's unary, so that it goes in front. Okay? Now, and then we have these a long list of binary operators. And so we're going to do, first we're going to do equals. And the next one we're going to do is three. Really equal. This one is our old friend equals.
Equal to or equal to?
This one equals. And the way we say, and the way we're going to say this is equivales. So this one is equals, this is equivales. Now I'm going to say a lot more about this a little later, but for now, let's remember the following fact. Equals is for Booleans or numbers. Equals. For Booleans or numbers. Okay? Whereas equivales, does anybody want to?
Booleans only?
Yeah, good. Equivales is for Booleans only. Now, that's just something that you've got to remember, okay? Okay, so this equals for Booleans or numbers, equivales for Booleans only. This is reserved, so this one you can only use for Booleans, but this you can use for both. All right? Now, so those are I'm just going to list them. We'll come back and see how they work. in more detail in a minute. Now, each one of these can have a slash between it. Now, you know from algebra what equals with a slash through it is, right? What does this mean? Does not equal, right? So this is differs.
Veil.
Yeah, and this is does not equal veil. Okay, so
The same thing could be said if you use the unary operator, the not, if you put that before the equal.
yeah. Well, I'm going to write that down here in a minute. Okay, so so this one is differs from. But this differs from works. Now, what do you suppose differs from works for? Booleans or numbers. Booleans or numbers. And then this is differs from, but this is Booleans only. Oh, listen, we haven't even started. There's going to be more and more. Okay, now the next one is going to be this one. It's looks like a V. It looks like an uppercase V kind of. Okay. This one we say. This one is called disjunction. disjunction. And in English, it's the word or. Well, this is English also, but. This is the formal. This is this is the disjunction operator. Okay, and it's or, and then the other one, another one that's kind of the same, looks kind of like it. But it's upside down, so it looks like an A without the vertical bar.
Dang it, I drew the vertical bar.
Okay, and so this is conjunction.
Vertical bar. To make it A.
And the English word for this, anybody know? And. Okay, so there's or and. Okay, and now here's another one. It's two stems. It's a two-stemmed arrow to the right, and this is the way we say this. This is implication. And the way you say it in English. It's implies or therefore, yeah. Oh, some people have had logic before, I see.
There we go.
Implies. Now here's one that's not so common in other forms of other systems of logic that you might be used to in math. But in this class, we're going to use this one quite a bit. It's this, but turned the other way around. Okay, and this means follows from. All right? And there's two more that we're not going to use in this class very much, but I'll just put them here just for interest. We won't really use them very much at all. But one is called NAND. And NAND is the same thing as, well, if you say B NAND C, that's the same thing as saying not, parentheses, B and C. Are you with me? And this and is this and, right? And this not is this not. And this parentheses is there because if B and C is an expression, then parentheses B is also an expression, right? So, okay, and the other one is nor. Which is not or, yeah. So if you said B nor C, that would be not B or C. Now, these two are really not used very much in this formal logic, but in this formal logic, formal methods class with proofs and stuff. But this is very important at in computer circuitry. And in fact, if you ever take the computer organization class, you'll see that we will use these way, way extensively. And we actually, we'll hook up circuits in the lab and at the logic, it's called the logic gate level in computers. These are very important. But for this, I'm just mentioning it here. We won't use this very much, these two very much in this class. You don't even need to know these. I'll never ask you a question about these. Okay? Now, what does all of this stuff mean? How does it all work? So now we're going to see how all of this stuff works. Okay. And here's what we're going to do. Have you guys ever heard, has anybody in here ever done truth tables? You've done truth tables before? So this stuff might look a little familiar to you before. Do you remember doing truth tables for those? Okay, so what is a truth table? Here's what a truth table is. A truth table describes how each one of these operators works by showing what happens in all possible states. Now, what's a state? What's a state, Josh? What's a state? Hold on. List the variables and its values, right? So what a truth table does is it lists all the possible values that a variable with this operator can have, and it tells you what it can be. But each variable can only have how many values? Each variable can have how many values?
One.
No, how many? Two. Each variable could either be what? Have the value t or true or value false. You see, an integer could have value 1, 5, 73, 965, negative 400,786. They could have a bazillion different, more than a bazillion, an infinite number of values, right? Okay, but with Booleans, there are only two possible values. So, okay, so here we go. So let's take a look at at the truth tables for these. Okay, so first we'll do the truth table for not. Now here we go. If this is p, how many possible values can p have? Two. This is a variable. It's lowercase p, right? So it can only have two values, either t or f, right? Now, what do you suppose if p has the value true, then what do you suppose not p? What do you suppose the value of not p is? That's false. And what's the value? And if p is false, the value of not p must be true. So that's the truth table for not. Now, these you have to memorize. These truth tables, you have to have these committed to memory. Okay? Every once in a while when I ask you to, I'll indicate if something's really important for you to commit to memory, I'll tell you that, and this is one of them.
Are we actually going to have to write out the truth tables?
Well, you might have to use them. And I might occasionally ask you to write them out. Yeah, I might occasionally ask you to write one out. Yeah. Okay, so this is how not works. Okay, now let's take a look at the truth table for. Let's do equivals, right? We could just as easily say equals because right? Because actually here let me make this observation. These two have the same truth table. Well, there is no truth table if you have equals and it's for numbers, because numbers can't be true or false. Numbers are 5 or 8 or 10, right? But if you're using equals for a Boolean, then it has the same truth table as this. And same here. These two also have the same. Same truth table. Okay. So now let's do the truth table for equivals. Now, is the equivals unary or binary?
Binary.
So therefore, it's in between how many variables? Two variables. So now instead of just having one variable on our truth table, we'll have p and we'll have q. All right? And then over here, we're going to say what happens with p equivals q. Are you with me? Now, how many possible combinations do we have of trues, and how many rows will I have to do to have all possible combinations of trues and false for p and q?
True, false, false, true, false, false, true.
So how many?
4.
4. So there's 4. Now, here's how we're going to order it. We're going to do t, 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 f, f, t, f, f. And here comes a really crucial point. When you do your homework for next time, please, when you do your stuff, when you make your tables, I insist that you do it in this order, because the poor grader, if you mix these rows up and then we're trying to find out which row is which, it's really confusing. So let's always get into the habit of doing TT, TF, FT, and FF in that order in the table. Now mathematically it doesn't make any difference, right? As long as what goes here, if FT is up here and as long as that's up there, mathematically it's correct. But for our convention, let's have our truth tables always be in this order. Are you with me?
Sure.
All right. Now, what do you suppose this is? Equivales or equals? Look, are P and Q the same?
Yeah.
So what do you think P equivales Q is? True. Are P and Q the same down here?
Yeah.
Wait. Are they the same?
Yes. Yes.
Yeah, they are the same. So this is what? True. Okay. Are these the same? No. Are these the same? No. All right. That's the truth table for equivales. Right? Now, here's another little thing. What about if you have a slash through an operator? Okay? So here's how that works in general. Anytime you have a slash between an operator. So watch this. If circle is a Boolean infix operator, then this Boolean operator with a line in between it is defined as follows. Is defined as, okay, so if you have P and this with this in between it and Q, this is the same as this, let's say, means
negation.
Yes, means negation, parentheses, P circle Q. Very good. All right? Does everybody understand what we mean by this? How this works? Okay, and that works in general. So here's my question. What's the truth table for inequality? So suppose we have P and Q here, and we have P not equal to Q, not equivalent to Q. Now what's the order? TT, TF, FT, FF. Yeah? So basically, because this one is true, false, false, true, well, if you negate something, that changes the trues to falses and the falses to true, right? So this is going to be false, true, true, false. Yeah? False, true, true, false. Is everybody clear? Yeah? On how that works. All right. I don't want to erase, well, maybe we can erase this. Yeah, we'll erase it. I know what we'll do, we'll scroll. So far, we've got down to here. Okay. So now let's do OR. So here's P, here's Q, P or Q. So true, 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 false, false, true, false, false. Now comes, I want to convince you why what we're going to put down is the case. Let me think. All right. Suppose I say, I'm going to make a statement. Suppose I say, this board is white. Is that true? This board right here, is it white? Oh, come on, don't give me these shades of white. Yeah, yes, that's true. Okay, and how about this desk is black? Is that true?
Yeah.
That's true. Okay, now I'm gonna put them together. Now we're gonna say this board is white, or this desk is black. Now I'm asking for the truth of the whole thing. This is white, or this is black.
False.
Oh, we have a difference of opinion.
Because they're both.
I know, but okay. When you say or, actually, thinking that it might be false, it's not that unreasonable to think that it would be false, because what you're thinking is, when I say this or this, it's either one or the other, but not both.
Yeah.
But our meaning of the word or is
Either.
is either or both. Right? Are you with me? And in fact, that's called inclusive or as opposed to exclusive or. But anyway, so here's the thing. If this is true and this is true, then this or this is going to be true. Is everybody clear on that?
Crystal.
Good. Now suppose I say the board is white or the desk is red. Now that whole statement
It's true.
is true because this one's white, even if that one's red, right? Is everybody clear? So this one's true. Now what if I say the board is red or the desk is black? Is that statement true? That statement's true. And now suppose I say the desk is red or the board is red or the desk is green.
False.
That's false. So how does or work?
If one's true, they're all true.
If just one, either one or both are true, they're true. And the only way the whole thing can be false is if they're both false. Is that clear? Are we good?
Yeah.
Now let's change it and do PQ, P and Q. True, 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 false. All right. Now check this out. Suppose I say the board is white and the desk is black. Is that true? Well, sure it is, because the board is white and the desk is black, right? So that's true. On the other hand, if I say the board is white and the desk is red, that's false, because it only just takes one of them to be false for the whole thing to be false. Are we good? So this is false. And obviously, if I say the board is red and the desk is black, that's false. And if I say the board is red and the desk is green,
False.
that's false.
Oh, really?
The exact opposite of or.
Wait. It's not the negation of this.
I know, but it's like.
It's just,
Like, they're both false.
Two variables.
It's just more
With
picky.
two variables it is, but with multiple.
it's more picky. Yeah, Kyle says, he says, yeah, and is more picky than or, right? Because the only way for it to be true is they both have to be true. But with this one, yeah, it is more picky. That's a good way of looking at it. I never thought of it that way. There's a lot of truth to that. Yeah, truth.
Wow.
Okay, so that's or and. Okay, so we'll scroll down here. We got or and. Now this one, watch this. P, Q, P implies Q. True, 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 false, false, true, false, false. And now, yeah, and P implies. Now let me tell you in English another way to say P implies Q. Another way to say this is, let me do this. P implies Q. Another way to say this in English is if P, then Q, right? Now, I'm going to use a little illustration to try to convince you why we are defining these operators this way. And here's the example. I just happen to really, I've never owned one, but I've always wanted to own a big red Corvette. I mean, for some reason, you know, ever since I was growing up, they were hot cars, and they're still great cars. One of the few American-made automobile products, I think, that, you know, really. Okay, so a big red Corvette. Unfortunately, I don't think I have enough money to buy one. On the other hand, if I were to win the lottery, then I would buy a big red Corvette. Yeah? Now let's think about that. P is winning the lottery. Q is buying a Corvette. And what I just said is that if I win the lottery, then I will buy a red Corvette. Are you with me? If I win the lottery, then I will go out and buy a red Corvette. That's the statement. That's the whole statement, right? And either one or both, or, you know, and we have these four possibilities, right? All right, is everybody with me on this? Now, here's what's going to happen. So here's the first scenario. You're standing out, you know, in front of your house or something, and I drive up in this big red Corvette. And you say, Professor Warford, what happened? I said, well, I won the lottery. And they said, where'd you get this red Corvette? And I say, I bought it, right? So in that scenario, I did win the lottery, and I did buy the Corvette. So my question is, when this statement, if I win the lottery, then I buy the Corvette, is that a true statement with that scenario?
Yes.
Yes.
It is. So everybody agrees that this is true, right?
Yeah.
Now let's take the second one. Suppose you're standing out in front of your house, and I run up to you and say, hey, I won the lottery. Look, I won the lottery. And you say, well, what'd you do? I said, well, I bought a new computer. Well, what else did you buy? Well, I bought this. Well, did you buy a red Corvette? Well, no, I didn't buy a red Corvette. Okay, so here's the scenario. I won the lottery. I didn't buy the Corvette. Now let's think about the truth of the entire sentence. If I win the lottery, then I will buy the Corvette. Is that statement true under those circumstances? That's not, you're right, that's false. And why is it false? Because I said, if I win, because the statement says, if I win the lottery, then I will buy the Corvette, right?
Yeah.
But I won the lottery, but I didn't buy the Corvette, so that statement, that makes that statement false. Is everybody clear on that? So this is false. But now, sports fans.
True.
Hold on, yeah, hold on. Yeah, what if, yeah, you're spoiling this is like the movie, what is that, spoiler alert? You know, come on.
He was dead the whole time.
Okay, this is like a spoiler alert in the movie, in the movie reviews, come on. So, you know, work with me on this. So, here's the next scenario. Suppose I come to you and I drive up in this great big red Corvette, yeah? And you say, whoa, Professor Warford, you got this big red Corvette? And I said, yeah. And they said, well, did you win the lottery? I said, no. But you got this red Corvette? Yeah. Did you win the lottery? No.
Drugs.
No, I have a rich uncle who died, and maybe I inherited some money, and you know, right? Okay, now here's my question. Here's my question. Is the statement, if I win the lottery, then I will buy a Corvette, is that whole statement true or false?
True.
Yeah.
Because then you'll buy another red Corvette.
Because well, no. And even if I never buy a red Corvette ever, I mean, and that statement is still true.
Until you win the lottery.
It can't be disproved until you win the lottery.
And don't, exactly. So this one is true, but now what about this?
True. If you don't win the lottery, you won't buy one.
Yeah.
If I don't win the lottery and I don't buy the Corvette, then if I win the lottery, then I buy the Corvette, is still what? True. Now, there's only one way that if P then Q can be false, and that is if P is true and Q is false. That's the only way that it can be made false. And usually I get more controversy whenever I present this to, but you guys must be superior. Yeah, your question?
Okay, you know how with like with negation and the and or,
Yes.
How you can use like, you can do multiple variables in a list, like this, and this, and this. And
Yeah, because an expression can be,
Yeah, how does that work for like?
yeah, we'll do some example. Exactly. We'll do,
Yeah, I imagine that gets a lot tricky.
yeah, well, no, it works, and we'll do some examples that mix them up, right? Now let's do the follows from.
Breakfast or math major?
Oops.
Breakfast.
Breakfast
P, Q.
Isn't that after?
What's that?
That sucks.
Okay, now, check this out, you guys. P follows from Q.
So Q.
Look, in algebra, what happens if you say, 5 is less than 13? I mean, everybody knows that this is the same thing as what?
13 is greater than 5.
13 is greater than 5, right?
Sure.
In fact, this just means this the opposite way around, right? Are you with me? So what do you suppose this is? P follows from Q is the same thing as what?
E implies Q.
No. Q implies P,
Yeah.
right? So my question is, if this one is true and this one is true, it's what? It's true. If this one is true and this one is false, that's the same thing as this, right?
Yeah.
So that's what? That's true. And this one is what? False. And this one is true. Does everybody get that?
Yeah.
Right? Okay, so now our author has done something interesting. He has combined all of these into one big massive table. And in fact, you can see there's true, 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 false, false, true, false, false. Notice that they're in our nice canonical order. And the or is true, 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 false. The and is true, false, false, false. Are you with me? The equals and the equivales is true, false, false, true. And the not is false, true, true, false, right? And then here's the implies true, false, true, true. And here's the false from true, true, false, true,
Did you
right?
erase the ones we don't know yet?
And these other ones are, they are possible binary operators, but they're not common enough to have names for them. And as it turns, how many possible binary operators are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, how many? There's 16. There's actually 16 possible Boolean operators that you could define if you wanted to, but the ones that are important, and he put them all. He just listed them all out here, and we just don't have symbols. We just didn't give the name for this Boolean operator. You know, are you with me? So anyway, I think it's a little confusing to have that one table. I kind of like to do it like this. All right, but now here's the question. The next question is, what happens if you have a more complicated expression? For example, what happens if you have 3 variables and you have a complicated expression like this? Okay, so what happens if you want to calculate the truth table for P or Q and not R? Right? So here's P or Q and not R. Well, what you do is you just do it a pair at a time. Right? So look. But now how many possibilities of P, Q, and R are there? It could be TTT, TTF, TFT, TFF, FTT, FTF, FFT, FFF, right? So now there's how many rows do we have now?
8.
We have 8 rows. Okay? So check this out. Well, first of all, what we do is we work on this not R, right? Well, so let's do the column for not R. Tell me, if R is TF, 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 then not R is going to be what?
False, true, false.
FT, 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 right? Like you just said. Okay. FT, 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 right? Is everybody with me? And what about Q and not R? So now what do you have to do? You have to take the Q column and the not R column, and you have to AND them together. So what will this be? Let's just name it off. False, true, false, false. Are you with me? False, true, false, false. True, false, false, right? False, true, false, 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 true, false, false, right? And now how do you do the P or all of that? Well, we just did all of that, so now what do we have to do? We have to take this column and do what with it? Or it. Take P or that column. So what do? We do this one or this one. So what's that going to be? True, 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 false. Oh, you guys are good. And now you say, you asked about what would happen if you had an equivalent, an implies. Well, you just do that with the, but you use the implies.
Is there a shortcut though?
No.
Because you know how, say you had 3 variables with ands in between them, with just and?
Yeah.
Then you don't even need to solve one at a time. You just be like, oh, if one of them is true, then they're all true.
Yeah, actually you can do that with and we're going to see why that works that way later. Yes, there are many shortcuts. There are many. Yeah, and we will learn them you will really learn them all. All right, good deal. See you then on Monday.